So welcome to everybody to this seminar, which is also included in the Road to CDC initiative, which is an initiative of the Italian chapter of Control System Society. So the seminar will be recorded and then put on the Italian chapter society YouTube channel. I will send you the link. So it's a pleasure for me to have here Alessandro Rizzo, and I don't want to spend too much time on the CV, but what I really want to stress is one thing is the eclecticism of Alessandro, and also is a globetrotter. So he got his laurea and PhD in Catania. Then he moved for a short period to University of Messina while working also with SD Microelectronics. So you will see this industry and academic, the two sides on the medal of Alessandro. Also, he's working on complex system networks, and while today is introducing you to epidemics, he's also working on robotics, automation, and planning. He also holds by the way, he is associate professor at Politecnico Torino, and he holds also a position as a visiting professor at the NYU in New York. He, as I was mentioning, he has this two sides aspect of excellence, both in industry. He got 2 Amazon Research Awards. He has also the NSF US Foundation project. He worked with team and other companies, as I mentioned before. And he got also best paper at IFAC, which is one of the most important best paper for application one at IFAC, which is one of the most important conference in our field. So I asked him to come here and to give us an overview of what we learned about epidemics and COVID. So the presentation, I guess, will be a little bit higher level, not only about his research. So thank you very much for being here.
Thank you. It is a pleasure and an honor to be here, and thank you for having me. So as Luca said, this is part of an initiative called Road to CDC 2024. The most important conference in control systems and control will be held in Milan this year. And so we thought, as the Italy chapter, to organize a series of events, a series of seminars to introduce people to CDC. And also there is a prize for a master thesis, to which a master thesis student can apply for thesis in systems and control. You get a link. The prize is 10, we have 10 prizes, 10 free registration to the conference, plus the possibility of presenting the work of the student at a dedicated workshop. So I think it's a great opportunity for young students. And as a part of the initiative, we also have some gadget there, t-shirts, pins, and the call for thesis prize. So at the end of the seminar, help yourself, take a t-shirt, take a pin, take whatever you like. So without further ado, let's start with our talk on epidemics. So today I'm going to give, I've been working on epidemic modeling for now more than 10 years now, starting from a background in network science. Then at some stage, I realized that, I mean, not only me, the whole world realizes that network science and epidemic science went side by side. So I myself started to delve into epidemics. It was an unfortunate season for the world because Ebola kicked in, but it was a fortunate season for me because I got a grant for epidemic modeling on Ebola. And so I started to work on that topic and never stopped so far. I mean, it's not worthy of mentioning that then COVID kicked in, so basically we never stopped. I hope we stop at some stage, but it's very unlikely. So today the title of the seminar is Epidemic Modeling and Forecasting, a Journey from the Cocktail Assumption. We will see what it is, to the advent of agent-based computation. So we're going to explore the whole spectrum of possibility of modeling and control epidemics with, of course, with our perspective of dynamical systems and control. So before I run out of time, I would like now to thank all the people that contributed to this work, because typically at the end of the seminar, you never have time, so you don't pay tribute, the right tribute to the people who work with you. So these are the guys and girls who work with me in the last 10 years. So I thank them very much. And this work, this presentation, of course, it's like it's being given by all of us. So as Luca said, my final destination for the moment is Torino, where I established a lab that is called the Complex Systems Laboratory, where we deal with many aspects of networked and complex systems, ranging from robotic, biological inspired control, network science, epidemic. You can have a look at the website. It's CSL, complexsystemslab.polito.it. Okay, so what is our journey today? We'll start by talking about forecasting and modeling, having a global idea on what forecasting epidemic means, what are the implications of forecasting epidemics and modeling epidemics. Then we'll start with our super basic epidemic spreading modeling, which is the one that I call the cocktail assumption, so where people are supposed to mix in sort of cocktail mixer. And then we'll start, this is of course an ideal model, because it doesn't exist any community in which everyone is in contact with each other, at least, I mean, in our real life. And then we'll start what I call the path to reality. So we'll start to introduce layer and layer of complexity to complicate our model, to make it more adherent to reality, little by little. So we'll talk about the static network assumption, the activity-driven network assumption, the metapopulation assumption, then the agent-based models, and then what we call the modeling hubs or the stack model. Okay, let's start with forecasting and modeling. So before 2020, possibly our idea of forecasting was only this one, forecasting weather, more or less. So typically, we look at a map, we have some physics equation about the weather phenomenon, and then we realize dashboards with the trend and with the key parameters of weather forecasting. After 2020, we got used to a new kind of geographical forecasting and modeling, which is the one related to epidemics. Of course, the driver was the COVID, but then since then, the surveillance and forecasting tools have been invading our let's say everyday life, more or less. So here you see a geographic prediction of or modeling of the whole of the worldwide spread of COVID-19. And on your right hand side you see a dashboard with the relevant figures. So it looks like the two elements, the two fields of prediction and forecasting have many things in common. Actually, they have very little in common. So typically what happens in weather forecasting is that weather is regulated by very complex equations. We know for a long time, we've been knowing for a long time now that these equations are also chaotic, so they are strongly dependent on initial conditions and parameter variations, and that's why we can predict weather for a long term. On the other hand, the equations that describe epidemic basically are quite simple. Those equations that you see, for example, in the board are widely used to simulate seasonal influence. This is called, we will see afterwards, SIR model, okay? But there is a key factor. These equations are not chaotic. They admit typically one equilibrium, and so they are very easy to study. But the problem is that this equation here that you see in the board is not super realistic, and there is a driver that makes these equations, or the equations that are used to model epidemics, very difficult to be used for forecast, and it's human behavior. So the human factor is the confounding factor, the complexity factor in modeling and forecasting epidemics. It's not the complexity in the equations, it's the complexity in the human behavior, which is, of course, unpredictable, not fully rational, dependent on culture, dependent on customs, etc. So, in both cases anyway, the questions we would like to answer are more or less the same. So, when an event will occur, where it will be located, how fast and when it will spread. So these are the basic questions. There is a bonus question that holds only for epidemics. Typically, we can't control weather. We can try to control epidemics, and the question is which intervention policies are best suited to control epidemics. And this is due to the fact that we can, in some way, control the behavior of people. So behavior is an element, of course, of complexity for the model, but it's also an element of control that we don't have in weather. The roadmap for setting up a forecasting in epidemics is the same similar to many other modeling activity. There is a model selection. There is an analysis of the available data. We do the inference of the parameter. We do a calibration. We do a validation phase. We can do forecasting. We do some assessment. And if necessary, we go back to step 3, 2, or even 1. So sometimes we put under question also, we question our model. Most of this talk here will be dedicated to point 1, to the model selection. So today I will give you an overview of the models that we've been using in our research, and then as long as I describe the model, I will give you some hints on the other activities. So the model in epidemics, similar to many other phenomena, start from the very coarse one, so a few equations, very approximated, a few parameters, very explainable, but far from reality. When we want to go towards reality, we're going to have models that are very granular, very accurate, very precise, with many parameters, but they're typically not interpretable. So, and one of the key commitment of my laboratory is trying to stay in the middle. So our research, our driver in research has always been trying to find models that are complex enough to explain many of the phenomena in the epidemics, but simple enough or well-structured enough to be studied also from an analytical point of view. So let's start with the simplest one. So the one that I call the cocktail assumption or compartmental model that relies on the fully mixed option. Okay? Fully mixed assumption means that we assume that people are all in a community, and basically in a short time everyone can communicate to everyone else. Everyone is exposed to the possibility of a contagion. So here we can assume that there is a population that is fully mixed, so we can talk about fractions of the populations in a lump sense that get infected. And what you see in the board is a typical model that we call SIR, susceptible infected recovery. And this is the model that, for example, we can use for seasonal influenza, that whereby when you recover, you are immune to the illness, basically, then you will be susceptible the year after. And the model is described by those 3 equations that are very simple. This is the variation of the susceptible population, the variation of the infected population, the variation of the recovered population. Here you see a term that is the product of the susceptible multiplied by the infected. That is the one that regulates the contagion, that describes the contagion multiplied by a coefficient beta that we call the strength of infection. It is related to the probability of getting infected. It's not exactly the probability. It's a number that expresses how much we can transform how strong we can transform susceptible to infected. And in the equation of the infected, the equation of the I, our population of the infected increases by the same term, so according to the number of infected and the strength of the infection, and decreases by the rate of recovery, gamma, minus gamma I. It's a term that indicates that people are recovering and go out of the game. And then, of course, these three equations are related by the fact that S plus R plus I summed up sum always equal to the number of people in the population. So this is a very simple model based on nonlinear ODEs. That is, in the figure you see the typical trend of this model. So there is a peak where we have a peak of infected people, and then the illness goes away spontaneously. Now, let's study how and when things get bad. Okay, so let's study how an epidemic starts, because with these equations, depending on the parameter, we can even not start the epidemic. We can remain at zero, or we can have an epidemic that extinguishes very fast. Or, similar to COVID, we can have an explosion of cases. How these things work? Well, we can start with a very simple assumption, and studying when everything happens here. Okay, when we are in the early phase of the illness. When we are in the early phase of the illness, we can make the assumption that the number of susceptible people is almost equal to the size of the population. So we can simplify our equation for the infected, that becomes what you see there, di by dt, but beta minus gamma I, which can be easily solved, of course. And if we solve this equation, it becomes I of t, that is the trend of the infected, I of 0, initial state, e to the gamma, beta divided by gamma minus 1, multiplied by t. And that beta minus gamma makes a difference. So you can imagine that beta minus gamma, when it's greater than 1, we have the illness that starts. When it's less than 1, the illness extinguishes very fast. So we have this parameter that is very important, beta divided by gamma, strength of the infection divided by the rate of recovery. And this is called R naught. This is the infamous basic reproduction number we've been hearing a lot. We've been listing a lot when we were talking about COVID. There is a basic reproduction number. People were engaged in explaining every day what this basic reproduction number was, and for COVID was slightly more than 2. An epidemiological definition of the basic reproduction number is the number of secondary cases generated by an infection in a totally susceptible population. So in the very early stage of the illness, the number of people that I can to whom I can transmit the illness at the beginning. It is meaningful in the first phase of the epidemics. Of course, it helps to discern between the exponential growth of the epidemics or its extinction, its fade out, and it can be computed in the field. Actually, it can be computed experimentally, especially at the beginning of the infection. That's what epidemiologists did at the beginning of the epidemics. And of course, it could be put in direct relationship with the epidemic parameter. In fact, with it, beta divided by gamma in our case. That is not always easy, but we can do it. And also, it can guide us through the selection of policies to contain the illness. So, for example, in our very simple case of the SIR model, to mitigate the impact of the illness, we can try to lower down R naught and making it less than 1, and we can do it in 2 ways: lowering beta or increasing gamma. Lowering beta means reducing the probability of infection, for example, keeping people at home, wearing masks. Gamma, reducing the frequency or increasing the time in which, shortening the time in which I recover, or keeping me away while I'm recovering. Okay, and that is the meaning of shortening gamma, or vaccinating people. This parameter here, the R naught, doesn't mean mortality at all. So these concepts are totally different. Infectiousness is different from mortality. So here you see a nice graph from the CDC, the Centers for Disease and Control in the US. You see, for example, that COVID is located here. COVID has a relatively low transmissibility and contagiousness and relatively low mortality, but there are other illnesses that have different behavior. So for example, very contagious but with a very low mortality, or contagious as much as COVID but much more deadly, like for example the Ebola, the HIV untreated, the rabies, etc. However, the R naught is not the only parameter that we need to control, to model and control an epidemic. That is what we call R naught is a potential infectiousness. As long as the epidemic progresses, the number of people that are susceptible are less. Okay, so basically, if I keep the R naught at the same level, my effectiveness in contagion becomes less. That's why maybe a more interesting parameter in the middle of the epidemic evolution is what I call RT, the effective reproduction number. It is the, let's say, the instantaneous version of RT, and it's given by the basic reproduction number multiplied by the number of susceptible persons. And this is actually what we want to tame, what we want to put down when the epidemics is evolving. And of course, if we didn't succeed, or in combination with trying to tame the basic reproduction number, another way to tame the illness is also to keep down the number of the susceptible population. And this is typically done through a vaccine. Okay? We tend to lower down the people that are susceptible in a way that RT tends to 0. SIR is not the only model. For example, there is the SIS for those illnesses where I can get infected and get back to the susceptible, then get infected again and again and again. Here, the equations are only 2, and typically this system has 2 possible outcomes. One is the extinguishment of the illness. The other one is the settlement of what we call an endemic phase. So more or less a constant number of infected individuals over time. And the difference between these two behaviors is driven by another ratio, which is another threshold, which is lambda divided by mu. Again, strength of infection, rate of recovery. In both cases, we have a threshold behavior. So this concept of threshold is ubiquitous in all the epidemiology. There is always, most of the time, a threshold, a certain combination of the epidemiological parameter that discriminates when I have a certain evolution of the epidemics, when I have another evolution of the epidemics. So for example, in both the SIR or SIS model, if beta over gamma or gamma over mu is less than 1, everything is going fine. If it's greater than 1, then my epidemics is spreading into the population. Of course, this is the very simplest form of threshold, but the threshold for more complex formulations of the models are more complicated. And also, the 2 progression models, so the models that I show, that show how the illness progresses in a human being, SIR or SIS, are the simplest that we have in epidemiology. Typically, models have many more compartments that indicate many more states in the progression of the illness, and also many options, for example, for treatment. So what you see, for example, in the left-hand side of the slide is a progression model for Ebola. On the right-hand side, 2 different progression models for COVID. The one on top contemplates 2 strains. The one at the bottom contemplates a lot of treatments, different treatments, for example, at home, in the hospital, in the intensive care unit, etc. Okay, so let's try to start now to complicate our model. So typically, we are not in a shaker, we are connected through a network. So we contact people in a certain in a certain environment and we make contact with a certain number of people. So a more accurate way of modeling contacts is through a network. In this case, the infection can propagate only through the existing links of the population. It is possible to both simulate the model and to do some analytical treatment of the model. And we have important results for this kind of systems, especially for the threshold, both for the SIR and the SIS model. So for both models, for example, the threshold of the same threshold as before, now it's not just a ratio of lambda divided by gamma, but it's proportional to the largest eigenvalue of the adjacency matrix of the network. So which basically now relates the possibility of contagion to the structure, to the topology of the population. And a fascinating hypothesis, which has been partly verified, there is a huge debate around it, but in practical sense, it's been verified, is that the distribution of the number of people that each individual see is not centered. It's not like normal, but it is what we call a fat tail distribution, following a power law. It means that there are few people that have lots of contacts. Okay, so basically we have a sort of hub topology in social networks, and if we adhere to this assumption that the populations are hub centered, this is going to be a good opportunity for viruses to spread, right? If there is a hub, if the person gets sick and it's the center of a hub, a famous person, a professor, a priest in a church, someone who is central in the community will spread a lot. These guys, these elements are called super spreaders of the epidemics. In this case, an important research group has found that if we compute the epidemic threshold, in this case, this is always related to the largest eigenvalue of the adjacency matrix. But this largest eigenvalue, in turn, is proportional to the average degree divided by the dispersion of the degrees in the network. And since we have a lot of dispersion, because we don't have a bell, but we have a power law, so we have a variance that basically diverges to infinity, the threshold tends to zero. So if we have a community where there are hubs, there are super spreaders, of course the threshold doesn't go mathematically to zero, but the threshold lowers a lot. So typically in society, in groups that are hub-centric, where there are hubs, the phenomenon is that the threshold for the spreading of epidemics lowers a lot. Okay. We can do a lot of reasoning about these models, and there is a bunch of literature in the net for like done in the next in the past 20 years or so. So we understood a lot from this framework, but then we realized that this framework was not super realistic again, and we made another step. So basically now we started from the cocktail assumption, everyone is mixed. Transitioning to the network assumption, we have a fixed number of contacts. So we are like in a calcio balilla, I don't know what is the name in English, but we have always the same number of contacts, but the most realistic assumption is like we are in a football field where we contact people, we get in touch, we can transmit the illness, go away, contact someone else, etc., etc., etc. And this is today extremely valid because we travel a lot, we move a lot. Maybe this was not the case in the 19th century, in the 18th century, where there was, for example, very dangerous illnesses, but they were confined in villages because people didn't travel a lot and weren't fast to travel. So basically, typically, if you got the Black Plague somewhere and you travel, typically you died before reaching the next village. Today, it's not like that. You get COVID, you get Ebola, you take a flight, you don't even realize you're sick, you go somewhere else and you infect someone else. So we need what we call a time-varying network model for us. So typically, we need more elements. We need a mobility model. So we should know how we move. A contact model. We should model how we get in touch with people, and then we need our epidemic model. The problem with mobility model is that they are very difficult to model because they are extremely complex, and they generate a particular time-varying network with spatial characteristics, which is very difficult to model. That's why people started to embrace the framework of time-varying networks, but then they worked at what we call the time-scale separation assumption. So either the disease dynamics is much slower than the connection formation. So basically, we are in the cocktail because we move a lot, and the epidemic is lower. Okay, so we are in the cocktail, or the other way around. The disease dynamics is much faster than the connection formation. I get the infection, I have the transition to the different states, I die or I recover before I move. So the network is quenched, okay? My research group, together with others, wants to stay in the middle. So what happens in between? Do we have paradigms to stay in between? So timing for moving, for traveling, compatible with the timing of illnesses, days. And this is the typical time scales that we are looking at. Travel by flight, by train, by car, commuting. It's a matter of hours, if not days. And the time scales of the epidemics are typically, or the known epidemics of nowadays are typically days. So that's why we used a well-known, unknown paradigm that was introduced in 2011 that is called activity-driven network, and we adopted that paradigm to develop epidemic models. Activity-driven networks are a particular time-varying networks where there is no motion, but where there is a parameter that is called activity, that represents the attitude of a person of making contacts. So basically, there are persons that are more active. So when they are activated, they are activated more often than others. So they make contacts more often, more frequently. And there are persons that have less social activity. With this parameter that we will see, it's a probability, is called activity. In this case, we can mimic, we can parallel the mobility world with the activity world. So I don't let all these guys move in my plane, in my area, but I mimic just the connections. So I can get rid of the mobility model while studying a model that has time scales that are comparable with those of the propagation of the epidemics. I define this parameter that is called activity. Once again, I can measure it from social experiment given by the number of interactions made by an agent divided by the total number of interactions in the community. And so I can derive a probability distribution of the activities. And guess what? The probability distributions of these activities in social system, once again, is fat-tailed, like the one in static network. So there are a few people that have an enormous activity, and there is the majority of people that have very limited activity. The fact that there are these people with this huge activity complicates things a lot. So that's how it works, the network. We start from a disconnected network. At each time instant, people that are activated with their own probability, which comes from the social analysis, throw connections, fixed number of connections are random in the community. Through these connections, the illness can transmit, and then we reset the network and we pass to the next step. Okay, so here we are mimicking the fact that we are going around and contacting people, okay, but without explicitly putting the geography into the model. We found a very interesting solution, very interesting observation. So the threshold between the two hypotheses, so between the shaker assumption and the frozen network assumption, the threshold that we found in activity-driven network is different, okay? And it's something in between, again. It has to do with dispersion, once again, because it's, at the numerator I have the average value of the activity, denominator, average value of the activity plus the square root of the dispersion of the activities. So it has to do with heterogeneity in the population. The more heterogeneous in the population, the lower the threshold, but this lowering is not as immediate, not as drastic as in the super spreader case. But this threshold is lower than the cocktail assumption. We were not happy because now we had to introduce behavior. As I said in the beginning, we want to introduce behavior because we know that behavior is key to model epidemics in a realistic way. So how we did introduce behavior in our model with activity-driven networks? By modulating the parameter of the activity. So basically, we change it in a time-varying fashion. Now I'm going to show the model, but just to give an idea, there are protections like wearing masks that reduce your probability of getting sick. So for example, the probability of infection went down, can go down in our model from a lambda to a lambda minus. And this mimics the fact, for example, that I put masks. On the other hand, I can decide to stay home. If I stay home, I reduce my activity. So I reduce the number of times that I get in touch with people. So also my activity can be reduced from a certain A to a certain A minus, according to some rules. For example, a behavioral change that could be introduced in a mathematical model, in our mathematical model, is to reduce our activity by a certain factor, either S for the susceptible, either I for the infected, according to my state of health. So if I am sick, I reduce my activity, I stay home. In this case, if I do all my calculations, I find a new threshold in my model. The new threshold is more complicated. Once again, it depends on the dispersion of the activity, but it's modulated by the parameters eta that regulates the change in my behavior. And as you can see, you can study the behavior of the threshold in our new formulation that decreases as long as the intervention or your behavior is much more pronounced towards, for example, a stay-at-home behavior when you're sick. And of course, I cannot go into the mathematical details, but this is the key message. We can find, we can model behaviors, and we will find different thresholds for the epidemics according to different behavior. Of course, we are going to validate all of this on experimental data. And to do this, what we did, we started, as I said before, to work on Ebola, on the West Africa Ebola outbreak, a very sad and dangerous outbreak before COVID. So thousands of casualties in West Africa, and there was a challenge for many aspects, a very complex epidemics because of the behavior, because of the large population, because of rituals, traditional funerals, uncertainty in the parameters, uncertainty in the reporting cases, etc., etc., etc. So very tough modeling activity. So just to give you the ingredient, we used activity-driven networks with this progression model that contemplates, for example, the traditional funeral, the exposed state, which is the incubation period, the hospital, recovered and died, recovered for good. And the model has a lot of parameters, a lot of transition rates, a lot of probabilities. It's very complex already, the progression. And what I'm going to say, this is the typical way we work in epidemic models. We don't do the identification of the whole parameter set because the parameter set is huge. So we will for sure incur overfitting. So what we do in epidemics, when we do real epidemics model, we talk to doctors, we browse the medical literature, we take the most of the parameters from the medical literatures, from the study, from the field study, and we just identify the parameters that are the mathematical proxies of behavior or other characteristic of the illness. Okay, so only the orange parameters that you see there, that are the exponent of the power law that describes the distribution of the activity, the average number of contacts that an individuals make in a day, and the two coefficients for the behavioral changes, which are abstract parameters, something that you would never know, are identified from data. The rest is taken from the literature. If we did doing this, we did our validation, we trained, we did the identification here in this area. We made the identification here, and we tried to estimate, to validate the model in the rest of the curve. The results were very encouraging. So with these results, and this is the other part, this is another key element in epidemic spreading, is projection of forecasting. So once you validate your model, the idea is projecting what-if scenarios. What-if scenarios, for example, what if we had more beds in hospitals? What if we started containment 1 month before, 2 months before? What happened to the casualties? Here, for example, and this was a very sad message that, that we had from our model, was basically we realized that if we started containment in West Africa 1 month before, the number of deaths would be drastically lower. And that's what we learned from our models, and what was also acknowledged then by the sanitary teams in the field. Just a couple of another quick insights. Another move toward the reality is that we are all on the move. So the next step was trying to mimic insert mobility in our model. So I don't want to spend time, you all made the COVID experience, understanding how geography was important, how it was important to contain the areas where COVID was developing. There was just a hub in Italy. You remember the two little villages, and then everything spread from there. So geography is extremely important, and we have to take account of that. So, and also the space, so spatial modeling is particularly important from containment and control. This is another reminiscence from the past. We started from controlling in the same way the whole country. And then we pass to the color system. The color system is a spatial containment strategy where the control is applied in a different way in different places. So now, including space in our model is of fundamental importance. How did we do it? Well, let me skip a couple of slides, and let me get here to what we call a meta-population model. So what we did to model the system is we divided Italy in all the provinces, 107 provinces that we call patches, and we devised a model that where the network is not the network of people, but it's the network of provinces. So we connected neighboring provinces through a network. Okay. In each province, we established an activity-driven model, the one like Ebola, but specialized for COVID. So basically, in the community of the province, we assumed that the population was had a behavior that was explainable by an activity-driven model, but then we connected these separate models through a network where we applied the commuting data. Okay, so we have some matrices that were representative of the travels of the community, and at each time instant we applied the travels. Okay, so we exchanged part of the populations to mimic people that were traveling from one patch to another patch. Of course, we don't have the time to go into the mathematical details of it, but each patch, each province can be represented by a set of differential equations, again, mimicking let's say the average behavior of the activity-driven model. So the system is of the order of 400 differential equations, not that bad to being simulated, and we found very accurate results. And here there is the possibility, of course, of doing a bit of analytical treatment, but also to project what-if scenarios that are dedicated to the geography. So in the end, let me skip the progression model and the results, we could have separated outcomes for regions or for provinces. And this, of course, can help policymakers in the field to understand where, for example, to apply mobility restrictions or activity restriction, where to issue stay-at-home orders and where not. For example, if you compare these two graphs, this is the graph of the outcome of the application of intervention in Bergamo province and in South Sardinia province. Same parameters, same nation, same situation, but because of the travels, the behavior resulting from the application of the containment policies is totally different. And we have to take this into account. So there are many things to do to complicate this model. This is part of the work that we are doing. I think it's 50 minutes, so maybe I will skip the agent-based modeling, which is something that deserves a bit of time to be illustrated. And I want to skip and talk about the next step that we did using the meta-population model, which is to unite our efforts with other modeling teams. So basically, some researchers realized that stacking up many models, creating what we call an ensemble model, and doing weighted average of the outcomes of all the models improves a lot the performance of the whole modeling. This is easy to understand, right? Because, I mean, if you average measures, you always obtain something better. But the idea is that these models here, the models that concur to the creation of the final results, are not all the same. So they specialize on some aspects. They have strengths and they have weaknesses. If we put them all together with all the limitations, the results of the ensemble is always better of the results of the single models. So we did the same thing. We used our COVID model. We tweaked it a bit because nowadays there's no more surveillance in Italy for COVID. So basically, we adapted it to what we call ILI, influenza-like illnesses. So putting together again influenza and COVID, because surveillance for COVID, specialized surveillance for COVID is over. And we participated to this distributed effort that is called InfluCast, where we stack all the models together. For example, here you can see the blue confidence interval is our model. The red, the confidence interval, is the ensemble. This is quite a fortunate case where our model was better than the ensemble, but nevertheless, the variance, the spread, it's less in the ensemble, and this is maybe even better to guess the average. So I'm proud of having guessed the average, but I prefer to have a model that has a slightly less accurate average, but with a spread, with a variance that is tighter, okay? Provided that, of course, the average is something that is reasonable. We participate to InfluCast, we participate to what is called Respicast, which is the European version of InfluCast. And also there we had very good results. So for the next season, we are going to participate again with our model, with an improved version of our model, with a Bayesian inference of parameters, and then also the commitment from the ECDC to give us mobility models, so to improve our model a lot. So what are our new efforts in this activity? We are already working on the bounded rationality of people. So what we are doing, we are, of course, on simpler models. We are working on using game theory to mimic what we call bounded rationality. So people do things that know that are bad for them, but they do it anyway. I know that smoking is bad for me, but I smoke anyway. It's your own cost balance that you put in your life. But this, nowadays, with all the propaganda of vaccines, etc., it's very important to be modeled, because it is not immediate that if there is a treatment, you're going to get the treatment. We're going to do modeling of dengue, which is becoming an emergency, especially in Brazil, for example. We're always looking for new models that conjugate accuracy and mathematical tractability. And we are going to apply rigorous control theoretical tools to devise strategies for timing the spread. For example, I didn't have the time to show it to you, but for example, we have a couple of papers on the application of model predictive control to tame epidemics. So, a couple of take-home messages before we part. Epidemic modeling is a complex matter because there is stochasticity, there is uncertainty in the parameters, there are human behavior, and human behavior is the key. The role of human behavior is a double-edged sword. It complicates things, but it is our control variable that we don't have in weather. So that is where we can go and act. There are different models from different data for different answers. Forecasting doesn't typically rely on a right model. One of the, let's say, skills of modelers is picking the right model according to the data we have and to the answer that we want to have from the model. A common trait among all models, something that I didn't talk about, is the limitedness of the prediction horizon. So we can predict up to a certain stage, similar to weather forecast. That's why, in a control perspective, strategies like MPC are very promising, because at least we have a short interval, quite short. For example, in our COVID model, it's 4 or 5 weeks. It's okay. We have a short interval on which we can predict. So predictive control can work. And the quest for us, as I said at the beginning, is attaining both high accuracy and mathematical tractability, because we don't want to rely only on simulations. Finally, just a word, we keep working on epidemic modeling because they are of great utility also in peacetime, what we call peacetime, because they help improving awareness and preparedness, that are two key epidemiological concepts. We must be prepared to the incoming of new epidemics. And also peacetime is a very useful time to also test other models. When you are in wartime, like when we were in COVID, we didn't have the time to test new models. We picked what we had and we worked with that. And we even, I didn't have the time to show you the agent-based model, but the agent-based model didn't have anything super clever and super mathematical, nothing. Just probabilities and SimCity. SimCity, the city, people inside, you make the move, you take the results. But the American government wanted forecasting, put money on the table, we did that, okay? And that is the wartime. When you are in peacetime, you can try many things. So on the one hand, you refine your model for preparedness. On the other hand, you can play with game theory, bounded rationality, etc., 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 and trying to be ready to incorporate them in the next way. Okay, I think I'm done. Of course, I ran out of time. So thank you again to my collaborators and colleagues, and thank you for having me.